Hi, welcome to my channel, JaberTime, where I do math videos from algebra to calculus and differential equations, simplified with examples. And I also do some videos on apps and programs. If you like this video and you want to see more, hit the like button and subscribe. And if you have any questions or comments, leave them down below. I want to thank you for watching and hope to see you again and again. Thank you. Let's talk about rules of differentiation. First rule is constant rule. The derivative of a constant is 0. d dx of c is 0. Derivative, that's what we call it, that's one way. The derivative of a constant function is 0 at every point because the values of a constant function do not change. This means the instantaneous rate of change is 0 at every point. Let me explain more. Imagine if you have f of x equals c, like f of x equals 5, excuse me, which is a horizontal line. If you walk, that's me walking, by the way. If you walk on the curve, which is a straight horizontal line, this way, and we usually go from left to right, from A to B, not from B to A. What's my slope? What's my rate of change? What's my delta y over delta x? What's my rise over run? It's always 0. Slope equals f prime equals 0. That's f prime. Okay, let's take some examples without graphs. That's the simplest, easiest rule that we have in differentiation. Keep that in mind. And this is at least why. If f of x equals 5, f prime equals 0. Notice that I have them all displayed. There is no need to slow down. If f of x equals pi, and pi for us is a number, f prime is 0. I keep saying f prime because that's how we call it, instead of the derivative of f of x, which is kind of lengthy. If f of x equals e, the famous number e, f prime equals 0. If f of x equals 7-Eleven, that's not the store 7-Eleven, that's just like the number 7-Eleven, f prime equals 0. If f of x equals 3.9 repeating, f prime equals 0. So it doesn't have to be like 5, so clear and so simple. It says if your function is a constant, the derivative is 0, and that explains it. Keep that in mind. My favorite one right here is actually e. You might think about 7-Eleven, right? I was thinking about it for a second. 7-Eleven actually. All right. Second rule, power rule. This is a power, x to the power n. How do you find the derivative or to tell the slopes of the curve? You bring this n up front. You reduce the exponent by 1. All right, that's how we speak. Practice. X to the second, f prime will be 2x. Why? 2 goes up front. 2 minus 1, you reduce it by 1, becomes 1. X to the 7th, 7 up front, x. Instead of 7 as an exponent, it's 7 minus 1, which is 6. X. Well, how do I do that? I don't see a number on top. Well, yeah, you see it. It's 1. You bring it 1, subtract 1 from 1, reduce 1 by 1, becomes 0. Anything raised to the power 0 is 1, so your answer is 1. How is that? Why this one is a little bit different? Let's take a look. I like math and I like concepts, and once you see things clearly, you start loving math, trust me. You see this y equals x, it's a 45 degree. That's me again. I'm trying to go up. As you can see, I'm having a hard time. Maybe I'm getting old, I don't know. I'm trying to go up. But I think my slope here or here or here or here or here is the same. It's the same rise over run anywhere you go. It doesn't change. And that's a 45-degree opening. That's a 45. Isosceles right triangle. The slope is 1. And that is 1. I think that helps also. See, any way you look at it in math, it's 1. I mean, we have to agree on the answers. If you look at it this way, formula-wise, graph-wise, it adds up and it agrees. Let's take another example. Square root of x. How do you find the derivative? Well, you gave me a clear example here. Now you're making it hard for me. Not really, but that's how we start. We start with simple, straightforward examples. But life is not always with simple examples or problems. Square root of x. How do you find the f prime? Well, let's look at this as a power if we can. Square root of x, differently it's called x to the power half. Okay, half goes up front. Half minus 1 because I need to reduce that by 1. Do the math. Half x to the power negative half. We don't like negative exponents for some reason. A to the power minus m equals 1 over a to the m. So you bring this down, make it positive. We don't like this look. I don't know why. 1/2 over square root of x. I think that's fair enough about the power rule. Here's another example just to support the meaning and what we're doing in rules do agree with pictures. F of x equals x to the second. Slope at 0, it's kind of hard to graph it on top of the black line. Slope at 1, those are called derivatives at single points or instantaneous velocity or rate. Slope at 2, slope at negative 1, slope at negative 2. Now let's do the calculations and see if it makes sense looking at the graph. F of x equals x to the second. F prime equals 2 times x to the power 2 minus 1. F prime equals 2 times x to the power 1. Plug in negative 2. Negative 2 times 2 is negative 4. Slope here is negative 4. Plug in negative 1. Slope here is negative 2. Plug in 0. 0 times x. Sorry. 2 times 0 is 0. That's slope of 0. Plug in 1. You get a slope of 2. Plug in 2, you get a slope of 4. I think it makes sense. Take a look. See this right here? Do you believe that the slope down here is 0 as tangents? Yes, it is. Look at the slope of 1. It's 2. Going up, positive, yes. I think this is kind of identical, but the other way. That's why it's negative 2. Because of symmetry from right and left. I think that's good enough. I don't want to keep talking about this graph, but just to give you an idea that what you're doing does agree with the behavior of the graph, slope-wise, as we discussed. Another rule, constant multiple rule. If you have a constant in front of your function, if that's how you want to call it, you could take the constant outside, out of your way. You see this? F prime. Let's apply some examples. 5x to the 4. You treat 5 as the c, and this is your function, kind of like another function, 5 times g of x. That's my function. 5 to the front. Now I look at x to the 4, and I want to find its derivative, 4x to the third. Simplify, 20x to the third. That's it. Sum rule. The derivative of the sum of two functions is the sum of the derivatives of those two functions. Too much to say, we don't like to say that much. Let's take a practical example. A function, another one, another one, another one, another one. So I have more than one function in our way. ddx of this much. We know how to do this, 5x to the 4. We just did that. Find derivative of this, plus 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 find derivative of this. Well, 3 is 0. It's a constant. What's the derivative of x? It's 1. What's the derivative of 9x to the second? It's kind of small here, but you can see from here. 2 goes up front, makes it 18, and this becomes 1. And the story continues, right? That's how you do it. Let's take another interesting formula. That's very interesting, by the way. The derivative of e to the x is the same. By the way, this is the only function in life that the derivative of that function is itself, actually. It's very interesting, and it's not our topic now, but just to let you know, the power of math in our life is beyond what you could see in just calculus. All right, keep that in mind right here. It's interesting, but it's not our topic. Just to give you more info about that, take a look. This is e to the x, exponential function. At 0 you get 1, because if you plug in 0, e to the 0 is 1, 0, 1. What this says, the slope of this blue tangent at this location is ddx of e to the x at this line, means at x equals 0 is e to the 0, which is 1. At 0, 1, the slope is 1. It's right there. It's the same as your output. The slope, because that is the slope, is the same as your output. And it looks like the slope is 1. What do you think? A 45 degree? You go higher, you get higher slope. Yes, e to the 1 is my output, which is actually my slope, about 2.71828. Next. So what I'm trying to say in general is any point right here will be x e to the x, and at that location ddx e to the x is always e to the x. Imagine a function at different levels, and you say stop as you walk on it. How high or how fast you're going up, like what's your slope? You go like, you know what, you just give me a minute, let me look at my y coordinate and I'll give you the answer. So that's one way to say it. Let's move on. Higher order derivatives. This is called second derivative of f of x. 2 tick marks. If you want to go like fifth, you're not going to go like 1, 2, 3, 4, 5. That's not practical. We use n with small parentheses on top to tell the reader that we are dealing with the nth derivative of f of x. How do you do the second? Well, you find the derivative of the first. You make it another time. How do you find the nth derivative? You go back and find it from the previous one. For example, if you need the fifth derivative, first you have to have the fourth derivative, then apply the derivative to that function, and that will take you one more, which is the fifth. Let's take a practical example after we see the notations. Those are new notations for us. F prime, one way to write it is dy dx, and sometimes we write y with a symbol like that. We call it y prime. F double prime, second derivative. That's how we write it. We write it this way. Nth derivative. That's how we write it down. All right. Let's find the third derivative of this function. 3x to the second plus 5e to the x. Here's the function. We need the third derivative, so we have to go first and second, then third. First derivative, this becomes 6x to the first. 5 goes up front. Then when I go in to find the derivative of e to the x, it doesn't change. That stays. Let's go another step. Derivative of 6x is 6, and that doesn't change. Let's do it one more time. That derivative is 0, it's a constant, and that doesn't change. That's it. Here's another example. 5x to the 4 plus 10x to the third plus 3x plus 6. Here's the function. Here's the derivative. 5x to the 4 becomes 20x to the third plus 30x to the second plus 3. And that is 0. Let's do it again. 3 times 20 is 60. 2 times 30 is 60. 2 becomes 1. 3 becomes 2. That goes away. One more time. 60x becomes 60. 60x to the second is 120x to the first. We're done. This is a lengthy problem, and I don't want to read the whole thing. I could, but it's time consuming. You could stop the screen and look at it. But let me give you a quick idea. City planners model the size of their city using the function a of t equals negative 150 t to the second plus 2t plus 20 for t that lives between 0 and 50, where a is measured in square miles and t is measured, or the number of years after 2010. Find a prime. What units are associated with this derivative, and what does the derivative measure? Why do I have this problem? Because I want to tell you that calculus is not just adding and subtracting and factoring derivatives, finding derivatives and things of that nature. It's actually in our life. Things change with rates. They speed up, they slow down, and so on. Population increases with rate. Money increases with rate, and so on. Anyway, look at this one here. Let's stick to A. Here's A. Here's A prime. We know how to do it. It's going to be square miles per year. Just go back to the reading. That's what they want. How fast will the city be growing when it reaches a size of 38 miles square? Here's A. This is my A. You set it equal to 38. You move the 38 to the other side, factor it, and solve. I get 10 and 90. We're just gonna take 10 because 9 is out of my domain. A prime is so and so. Plug in 10 and I get 1.6 square miles per year. How fast will the city be growing? It's growing at that time, after 10 years, with this rate, 1.6 square miles per year. Part C. Suppose the population density of the city remains constant from year to year at 1,000 people per mile square. This talks about miles per year, and this talks about people. So there's two things. So if you increase by 15 square miles, and every mile square gets 1,000 people occupying it, that's part C, all right? Determine the growth rate of the population in 2030. 2030, we started here at 2010, so we're going to do the math and use t equals 20. Plug in the numbers, read this if you want. 1,000, which I mentioned, times 1.2, which was done right here, and that tells you 1,200 people per year, because you got to consider the rate and how many miles you have. Next, I included this problem because I want to show you something interesting when it is pieces. This is called piecewise function, parabola to the left of 0, a different parabola to the right of 0. The first one has including the 0, right? Derivative will be x to the second plus 1, 2x, and 2x to the second becomes 4x. X becomes 1, and 1 cancels, becomes 0. But this is what I want to highlight for you. Equal sign in the original function. This is a corner point from the last lecture video, I told you that we don't have derivatives at corner points. This is a corner point, so no derivative. There is no derivative at corner points. Keep that in mind. Let's take another example. What about if they gave you this? Well, we don't know enough rules. We're using our rules now. There is a product rule, but that's in the coming sections. If you are giving this, all what you need to do is use the distributive and expand it. Then go after these functions one by one, and that should do it. Here's another example. X cubed minus x over x. If you use the distributive property, you divide this by this and this by this, assuming that you can, which means x cannot equal to 0, it's out of my domain. I get x squared minus 1, because we don't have a quotient rule. So we have to handle it with what we have. First derivative, 2 comes up front to the power 1, and this goes to 0, so we're done. Another example, x to the second minus 1 over x minus 1. All these are practice and techniques on how to do it. Factor the top part, difference between two squares. Cancel this. I get x cannot equal to 1, because if it's 1, it will make the denominator equal to 0. Since this cancels, we have a hole in the graph at x equals 1. And the simplified function is a straight line, but cannot have an image at 1. First derivative, or the derivative, will be, for x will be just 1, the 1 will be 0. What this means, it means that your derivatives are all the time 1. And you don't have a derivative at x equals 1, because 1 is also out of my domain. You see, you can't have a derivative for when the original function is discontinuous. We had that on the last video. Excuse me. Finding slope locations. This is an interesting problem, and it's similar to your assignment. I'll go over it quick. There is no need to slow down, and we'll take care of it. X cubed minus 27x plus 5. Find the value of x for which the slope of the curve is 0. That means we have horizontal tangents. That means the curve goes up, cubic, down, back up. When it's going to be horizontal tangent, when it's going to be horizontal tangent, that's when it curves back. Okay? That's this. Find the values of x for which the slope of the curve y equals f of x is 21. That's kind of high. So the curve goes up, down, back up. When it's going to be too steep, slope of 21 is going to be here and somewhere else. We'll see. First, for part A, this is our function. That's how we find the derivative. I think it's simple. Bring the 3 down, reduce it by 1. This goes to 0, that's minus 27. Set it equal to 0 because we want it to be 0. When the derivative is equal to 0, that's in other words, when my curve will have a max and when it will have a min. We set the derivative equal to 0 and we use algebra skills to finish it. You follow me? And I believe if everything is simple now, at 2 locations, at 3 and at -3. It's going to have a max here, it's going to have a min here, because I know this is going to start going up, back down, then back up. Max and min. Max actually at -3, because -3 is on my left. Okay, when the slopes will be 21, that's my derivative. I will make this 21 and use algebra to solve. You see, this is my derivative, which is clearly here written. I set it equal to 21 because I don't have another x, so I'm not going to use factoring technique and quadratic formula and all that stuff. All what I need to do is get rid of this, move it down here, divide by 3 after, and I get 4 and -4. Two locations at -4 and at 4. The graph is going up with a slope of a tangent of 21. That should do it for now. Thank you, and I'll see you in the next one. Thank you. Thank you for watching. If you like this video, subscribe and give it a like, and I'll see you in the next one. Thank you.